Hello. This is transition metals, and try and get through as much of this as we can in 30 minutes. Okay, so first of all, just a quick definition. We've got our periodic table, and we know that it's split up into these blocks where we're filling different subshells. So the D block is that middle block of elements where we're filling the D subshell. But transition element has a slightly different definition. It's a partially filled D subshell. So when we look at, let's just write the elements down: scandium, titanium, vanadium, chromium, manganese. So if we look at scandium on the left there, it's obviously in the D block, but scandium 3+ would not be considered a transition metal, or it wouldn't have the same properties of a transition metal because it doesn't have a partially filled D shell. Similarly, zinc 2+ doesn't have a partially filled D subshell, has a completely full D subshell. And the reason for that is when we start removing electrons, so if I look at zinc 4s2 3d10, when we start pulling electrons out of the D subshell, we always remove the 4s first. So zinc 2+, sorry, I missed out the argon here. Argon 3d10, there we go. Zinc 2+ would just be 3d10. So zinc 2+ and scandium 3+ don't share the kind of common properties that you'd expect transition metals to exhibit. The other important thing, apart from removing the 4s first, is good old crazy chromium and copper. That's right. So chromium you'd expect to have to be 3d4, but it takes one electron from the 4s to make 3d5, and the reason for that is when you put one electron in each orbital, that increases the stability of the subshell, and so on for copper 4s1 3d10. So you've got, again, 2 electrons in each orbital increases the stability of the subshell. Okay, so remove the 4s electrons first, and then crazy chromium and copper. Of course, the two work together as well. So copper 1+ would just be 3d10. Remove the 4s first. Okay? Okay so far? All right, so the key things that transition metals do that other metals like sodium or tin don't do. Oh, what are those key properties? Come on, pitch in. Colours.
Oxidation state.
Yeah, it's the one that doesn't begin with C. Although if you called it different charges, which isn't quite the same meaning, is it? But it does give you a C. Coloured ions, different charges.
Formed complex ions.
Complex ions. Good. Catalysts. Okay, they all begin with C, almost. Okay. Colours, complexes, catalysts, and different charges. Or it's better to say variable oxidation states, but if you can remember the 4 C's, that can help trigger that as a mnemonic. Okay. So let's do colour first, because it's a good self-contained little topic. Why do transition metals form colours? Or to ask the bigger question, why does anything form a colour?
Isn't it when like light travels through different subshells? From like
Forget the subshells for a moment. Just what is colour? You know, this is red because what?
it absorbs everything other than red.
Okay, so it has to absorb frequencies in the visible region of the electromagnetic spectrum. Lots of things absorb infrared light, lots of things absorb ultraviolet light, but we won't see those as colours because we don't detect those frequency bands. But if the substances absorb part of the electromagnetic spectrum, we'll see the other parts. And just to let's go for a beaker of copper sulfate. Here we go. And we can imagine our light coming in. I know that physics likes to have 7 colours in the rainbow, but really there's 3 bands of colour. Just look at how any television works. So white light contains red, blue and green light. What does the copper sulfate do?
Absorbs the green and red.
Absorbs green and red. So the reason that the D subshell forms these coloured compounds is the 5 orbitals in the 3D there can split. This usually happens when electrons go into it, so it's not split until we put some electrons. So that's what have I used in the booklet there? Okay. 3D8, so we're looking at nickel apparently. So I've got some electrons in the 3D. That would split the 3D to 2 parts. 3 of the 3D orbitals slightly drop in energy, 2 of the 3D orbitals slightly increase in energy. And what that does is allow more electrons to go down and fewer electrons to go up. Well, that creates these 2 energy bands, and in between those 2 energy bands there's that energy gap. Okay, so how does the energy gap relate to light? Well, I need maths. Question was, how does the energy gap relate to light? Okay, what's the equation?
Delta E is hc over wavelength.
Okay, so delta E equals hf or h nu is the first equation. And then frequency is, what is it? I can't remember the maths. F is c over lambda, isn't it?
Yeah.
That's it.
Oh.
Lambda is wavelength, c is the speed of light, h is the Planck's constant. So rearranging that, what have we got? Delta E equals hc over lambda. You're expected to take these into the exam in your head. Okay. Yeah, delta E is the energy absorbed, so h is Planck's constant, f or nu is the frequency of light, c is the speed of light, and lambda is the wavelength in meters. delta E is the energy gap in joules. So that energy gap, delta E, corresponds to a wavelength of visible light. So no, we've done nickel, haven't we? But if it was copper, then delta E would be absorbing red or green, whatever it is. So the electrons absorb the energy, get promoted upwards, and then come down. For complex reasons, the electrons don't just drop straight down and emit red-green light. The electrons kind of sort of potter back, finding other routes, and often the energy just goes out as heat into the solution. So if you shine light on something, it warms up, which is fairly logical. You're giving it energy, but the energy doesn't get emitted as light; it just gets absorbed as light. Okay, so we can use all of this to test for concentration in a process called colorimetry, not to be confused with calorimetry, which is measuring heat. Colorimetry works. It's a little box. I don't have an. It's a little box. You put a container of dilute solution in it, and then you pass light through. Usually you pick a wavelength that you know is going to be absorbed. So you might pick red light for copper sulfate, and you see how much of the red light is absorbed when it goes through. And the more concentrated the solution, the more light will be absorbed. So you can draw a straight line graph directly proportional concentration to what's called the absorption, which is just a measure of the amount of light absorbed, usually as a fraction of 1. And then once you've drawn that graph, well, now you've got it's essentially a calibration graph. You've calibrated your colorimeter. So now you could stick an unknown X into your colorimeter, read it straight off the graph and find out its concentration. That's how that works.
Just two.
Any questions about colour? Move on. Right, complexes. So there's a bit of language around complexes and a bit of geometry. If we have an ion, say we have copper 2, say we have a solution of copper sulfate, we know that ions dissociate if they're salts. So a solution of copper sulfate is never actually a solution of copper sulfate. It's a solution of copper ions and sulfate ions, and they would remain separate in the solution anyway. But the copper ions attract water molecules because they're charged, and we know that waters are also polar, so that the delta negative oxygen would be attracted towards the positive charge of the copper. But more than that, the oxygen has a lone pair, and it can donate that lone pair of electrons to form a covalent bond, also known as a
Ligand.
no, the type of covalent bond.
Coordinate.
Coordinate covalent bond. So we have, we just use that word ligands. So I'm just going to do. Okay, so the ligands bond via coordinate covalent bonds to the central metal.
Do you need to show it as an arrow?
Hey?
Do you need to draw it as an arrow?
Well, traditionally they are drawn as arrows, but if you're asked to draw the shape of this ion, then you don't need to. So that word ligand means what? I don't know how I've defined it here. What's that word ligand mean?
Is it like central atom?
No, the ligand is the thing around the outside. What's the ligand doing?
Coordinate bonding to the central transition.
By doing what?
Donate null effect.
Yeah, so they've got to be able to donate a lone pair of electrons. So they can be charged. So you get OH minus is a ligand, CN minus is a ligand. Or they can be neutral, like H2O and H3. And in fact, you can get some ligands which the only pair of electrons in the molecule is actually in the bond, and they'll attach from the bond. You don't need to know about any of those. To a central atom, metal atom. It's always a metal. Atom, ion. I'm going to go for ion. So we would write that as CuH2O, and then we put the square brackets around it to indicate that it's a complex, and the charge goes on the outside.
Will it be 6H2O? Or
Sorry, yes, 6 of those. Thank you. Yeah, do you have to name these things? Or do you just ever recognise the names?
isn't it like hexa, aqua?
Yeah, hexa, aqua, copper 2, that would be. Hi.
For a couple of signatures, please, sir.
So let's do a bit of geometry. So I haven't drawn it very well, have I? But that's 6 groups equally spaced is octahedral. We can have the usual shapes. So you could have copper 2 plus with what am I doing? Four chlorines around it, tetrahedral. And so on. We can also have square planar and linear, and so on. So one point of attachment to the metal ion is called what? As opposed to 2 points of attachment or 6 points of attachment? Monodentate. Dentate as in the dentist, as in biting. So monodentate only has 1 bite. Bidentate, 2 bites, so 2 lone pairs donated. So what are our bidentate ligands?
So there's 2 CH3s and 2 oxygens.
2 oxygens?
It's like O minus. Is that a different thing?
No. Well, ethane dioate. Has got 2 lone pairs, so it can attach to the metal from 2 directions. That's one of them. The other one's,
NH2.
yeah, the other one's got couple of nitrogens again, which can donate there. That is
What was the question say?
what's it called? Ethane diamine. That's right. Just remember the all-important rule. 007 says di has an E in it. So it's ethane dioate, ethane diamine. And then polydentate or hexadentate. 6 points of contact. The example being EDTA. You don't need to know the structure of EDTA, but you should be able to highlight the 6 lone pairs. So where are they? Oh, that's 4 minus, by the way, just put that in. On the 4 oxygens, yeah, so 1, 2, 3, 4, and the 2 nitrogens. So the EDTA molecule kind of holds onto the metal ion by sort of just grabbing hold of it with these 2 sort of arms which kind of come around and grab it, sometimes called chelating. I'll come back to chelating in a moment, but for reasons that will become clear, the reaction is driven forward. So it's a very good way of getting any metal ions out of a solution. You chelate them with EDTA. Yeah.
This was sort of the door, don't it? So that's got
because I got this part wrong, right?
Yeah, okay. I'm teaching at the moment. I'll have a chat with you next lesson. Yeah, a couple of other words that we need to know in relation to complexes. So we've already got the geometry coordination number.
how many bonds there are.
Yeah, number of coordinate covalent bonds. Not the number of ligands, right? So tetrahedral, the coordination number is 4, but for hexadentate ligands like EDTA, the coordination number is still 6. Yeah, we've still got 6 points of attachment. And there's one other word that we need to know, isn't there? Ligand, complex ion, shape, coordination number. No. Can't remember. Okay. Moving on then. Variable oxidation states. You're doing colours, you're doing complex ions, or we'll do catalysts last. Okay, so you should know a bit about vanadium. So vanadium exists as oxidation states +2, +3, +4, or +5. So just get these right. So the confusion between VO2 plus and VO2 plus, V3 plus and V2 plus. And they've all got different colours. So you can do a nice experiment where you stick some vanadium 5 on a stirry hot plate and add some zinc or later magnesium, and it'll reduce down. It starts off yellow, and then it goes, can remind myself about this, it goes blue, then green, and then purple or violet at the end. Quite a lot of transition metals have different colours that you should be aware of. So you might be aware of dichromate. What colour's dichromate? It's used in testing for alcohols sometimes. Think Lucozade.
Oh, it's the orange.
It's a really bright orange colour, and then it forms Cr3 plus. If you've got an alcohol there, acidified dichromate will be reduced to Cr3 plus, which is green. Similarly, we use copper 2 plus, a solution of copper 2 plus. You'll know it as Fehlings or Benedict's, depending if you come from a chemistry or a biology direction. It's the same stuff. Benedict's detects reducing sugars, Fehlings detects aldehydes. Reducing sugars contain aldehydes, so that's why it's the same test. Copper sulfate, or just copper 2 plus, is blue. What is it? What colour does it go?
Orange.
Bit more.
Red. Brick red.
Brick red, very nice. Brick red what? Precipitate, yeah. So that's copper 1. So it goes from the blue copper 2 to the red copper 1. Something else we can use to test for solutions is that permanganate. What colour is permanganate?
Purple.
Or we should call it manganese 7, really. It's the +7. And then we reduce that in acid conditions to Mn2 plus. It is colourless, well done. Unusually for a transition metal. Actually, if you get a jar of solid manganese sulfate, it's a very pale pink, so it does have a colour. But in the kind of dilute solutions you work with in the lab, you can't see it. You might also use iron 2 plus and iron 3 plus.
The titration you did where you used the banana pink and that one made it really pink. Yeah.
Well, I'll come back to the titration. I was going to say in a minute, but we're almost out of time. But in a titration, you're adding permanganate from the burette, which of course is purple, to your flask, which usually contains, say, iron 2 plus or whatever it is you're oxidizing. So as the permanganate falls into there, it'll go colourless because it's forming Mn2 plus. But the first drop of permanganate that you add that isn't reduced will stay purple, which will make the solution go pink. So that permanent pink colour is the end point of your titration. It's not because Mn2 plus is pink, it's because you've got a very dilute permanganate solution. Colours of iron 2 plus?
Rusty brown or green. Dead green.
Yeah, so that's pale green solution. If you were talking about the precipitate, then it's a sort of pond green. And iron 3 plus, aqueous?
Rusty brown.
It's not rusty brown. So rusty brown would be the colour of the precipitate.
Oh.
So the solution would be sort of think a diluted version of that.
Pale orange.
So yeah, pale brown, orange, yellow, depending on how dilute it is. Yeah. Okay. So yeah, a lot of these you're familiar with and you've come across before. Right, we'll just do 5 minutes on, 3 minutes on catalysts then. So catalysts fall into two broad camps, heterogeneous and homogeneous. What's the
Heterosis. No,
hetero means
different.
different.
Different states.
States or phases is the word that's often used, but yes, states is fine. So, for example, if we're catalyzing the Haber process, we use iron. So it's solid iron surrounded by gas. There's lots of other examples. SO2 to SO3 with V2O5 and so on. They're in the book. Platinum, palladium in the car. What's it called? Exhaust pipe, catalytic converter, and so on. So we've got a different state of the catalyst and the gas. How does it work? I mean, speeds up the reaction rate. Let's just spit that one out. It speeds up the reaction rate whilst not being used up itself. Okay, let's get that one in there. Also, so it does what by providing an alternative pathway?
Lowers the activation.
Yeah, lowers the activation energy by providing an alternative pathway. That's all fairly GCSE. What's the A-level extra bit? How does it actually do that? Here's my catalyst.
Something like bond with surface.
Yeah, so what do we call that bonding? So we imagine the nitrogens kind of attach to the surface of the iron catalyst. What do we call that attaching to the surface? So a sponge has holes in it. It absorbs water inside it. It adsorbs. Yeah, adsorption. So that's where the gas bonds or adheres or attaches to the surface. So it all works at the surface of the catalyst. That weakens the bonds in the molecule. For the case of nitrogen, that's very important. And then atoms can start to bond themselves onto those. Okay. So that's the old kind of the alternative route, if you like, that adsorption. Catalysts don't get used up. That's great, but they don't last forever. Why not? So what do we mean by poisoning a catalyst?
It's when all like molecules like impurities and stuff bind to it, and then.
So in the case of the Haber process, what's the impurity?
NH4.
Oh.
No water.
Sulfur. So sulfur sticks to the surface. Remember, the surface is where it all happens. That's the active site, if you like to use a bit of enzyme language. That's the active site of our catalyst. So if we cover the surface in a layer of sulfur, the gas particles can't stick onto it anymore. So eventually we just have to throw it away. It doesn't actually last forever. Yeah. Is that everything about that? Oh, that's that word desorption, which you'll sometimes see as well. If adsorption is sticking to the surface, desorption is letting go. All right, like that, letting go. Okay, and then homogeneous. I don't really have time to go into this, but homogeneous catalysis is when they're in the same states,
It's not
usually aqueous. So if we're trying to get two ions to stick together, well, I don't know how often this actually happens in industry. If we've got two ions that are both negatively charged, they're not going to attract each other, they're going to repel each other. So it's going to get very hard to start the reaction. So we chuck in a catalyst in solution that reacts with one of them and then forms an ion that reacts with the other, and so is formed back. So I haven't got time to go into that, we're already over. Okay, so that was a very whistle-stop tour. We haven't got anywhere near ligand exchange and
That's deprotonation.
so we'll have to do that next time. That was fun.